So, let me shortly recall what we've seen in the video. We have laminar flow and we have turbulent flow. And you see actually a picture here of cigarette smoke billowing up. And we see at the bottom here we have laminar flow, where the fluid moves in streamlines nicely next to each other. And on the top we have turbulent flow, where fluid elements randomly move one to the other and through the other. What is laminar flow? Well, laminar flow is fluid that moves in layers. So a fluid element like a smoke particle in this case will stay in its own layer, and the next smoke particle that's in the same layer will follow the same path. And you see, layers are laying next to each other. The smoke particles do not move from one layer to the other when it's laminar flow. They stay in their same layer. And these layers can move at different velocities. So you have, for example, a fast layer in the middle and a bit slower layer next to it. So what's going to happen is that these layers, there will be certain friction between the layers. We call that viscosity. And the main energy losses in the fluid stream will be actually the viscous losses, or the frictional losses between the layers. Now flow, in which the main energy loss is actually the frictional losses between the layers, that we call laminar flow. There will be flow in which the fluid elements move within the same layers, and the energy loss is due to friction between the layers. Now what is turbulent flow then? In turbulent flow, the fluid elements, they start in one layer, but they don't remain in one layer. In turbulent flow, the difference is that the fluid elements here in one layer can have enough energy to actually move from one layer to the next layer. And when they do so, for example, you get a fluid element from a rapid stream going to a slower moving stream. When they do so, they transport kinetic energy from the rapid stream to the slow stream. So the rapid stream loses kinetic energy and the slow stream gains kinetic energy somehow. So if we have a flow in which fluidic elements move between layers and actually transport kinetic energy between layers, we say that the losses in the flow are mainly kinetic. Such flow will be turbulent flow. So we have kinetic or inertial energy losses, and we have viscous losses in the flow. What are inertial energy losses? I can say that is this inertial energy that is relative to a mass times a velocity. And viscous losses is related to the viscosity of the fluid times the area between the fluid layers. And now I can work out that for a fluid element, its mass will be the density times its volume. And so I see that this is equivalent to this, is equivalent to this. And now here what I do is I say the volume scales to the third power of the length. The area scales to the second power of the length. So this one can be scratched out entirely, and here I have to take away the power 3. So I say that inertial energy versus viscous, so inertial losses over viscous losses, scales with density times length times velocity divided by viscosity. And this, if you print in a number, so this is density is kilogram per cubic meter times square meter per second, and the viscosity here, I forgot what the dimensions are for viscosity. But if you look at it, if you look at all the dimensions, you see that these dimensions all cancel out. So this number actually is a dimensionless number. It's just a figure with no dimensions, and that number is called the Reynolds number. And a high Reynolds number will mean that I have a lot of inertial energy losses compared to viscous losses. That means a high Reynolds number will mean that I have a turbulent flow. A low Reynolds number will mean that if I have a lot of viscous losses but only few inertial losses, so viscous losses are going to dominate. So a low Reynolds number means laminar flow with viscous losses dominating. And now there's something called a transitional Reynolds number, RET, and that's typically around 2000. It's not a fixed number, but typically people say a flow where the Reynolds number is above 2000 we'll call turbulent flow. A flow below 2000 we'll call it laminar flow. That's not written in stone. Basically you can say a flow wherever the Reynolds number is below, say 100, will be laminar, and when it's above like 10,000 it will be turbulent, and in between it's somewhere in between. But yeah, you understand. The higher the Reynolds number, the more turbulent, the lower the lower the Reynolds number, the more laminar the flow will behave. And 2000 is a typical value that is used as kind of the borderline between laminar and turbulent flow. What happens now on the microscale? Well, we have a Reynolds number is a density times velocity times distance divided by viscosity. The density of a fluid is independent of its size. I mean, it's basically how much it weighs per volume. Yeah, if I take a little bit of water, it has the same density as I take a big bucket of water. The viscosity of a fluid is also its material property as density. So it's also independent of the size. So the rho and the mu are independent of size. The velocity on the microscale, we're going to see systems on the microscale will be the velocity will be lower, and that is because we have much more friction, and therefore things will move much slower. So the velocity will be very little, and of course the dimension L is also small because that's exactly what we're doing. We're downscaling the system. So we have a system in which U is very small and L is very small. So we get a Reynolds number that is very small, always in the microscale. So typically microfluidic systems have a Reynolds number that is smaller than 1. So we say it's way below 2000, and because we have such a low Reynolds number, the flow in a microscale will almost always behave as laminarly. Therefore we can say microscale flow is like ketchup. So the flow in the microscale is laminar. That's the same as flow on the macroscale that is laminar. And flow on a macroscale, which flow is laminar? Well, that is flow with, for example, with a small density but a very high viscosity. So any flow with a very high viscosity, if the viscosity of the flow is high enough, the system will behave laminarly. So we have systems like, for example, ketchup has a high viscosity, honey, syrup, these are liquids with a very high viscosity. And so therefore, even on the macro scale, these very high viscous liquids will behave laminarly. So we can compare the flow on a micro scale behave similarly as the flow of a high viscous liquid on the macro scale. Yeah? So we can say, for example, if we think, for example, now as blood actually is a fluid, a watery fluid that contains a lot of blood cells, and these blood cells in the blood will basically behave like ping pong balls in ketchup. So fluidically they behave the same because ketchup has the same viscosity as has a very high viscosity, and ping pong balls have a very small inertia, just like blood cells, because blood cells are very small, they have a low inertia. Ping pong balls have a low inertia because they have a very low density. So we can think like blood cells in blood behave like ping pong balls moving through ketchup. So you understand that on the microscale, you know, things behave differently than you experience them on the macro scale, which makes it interesting, and we'll see that we can do a lot of different things with that. So let's have a look now at a first laminar flow in a microchannel. And the next video shows you that. This is a picture of the video. So you're going to see a video in which flow comes, different flow streams come to different color dyes. These are candy dye that they send through maybe 10 different channels from the top, and they come together here, and then they're distributed here. And you can see that the liquid will flow. The flow lines, they don't mix. The liquid remains in its own flow layers because it's laminar. So you see, for example, this orange line here will end up here, and this blue line next to it will remain blue next to it. So you see, you get this very nice direct flow patterns. Another thing you'll notice is that the video has music, and what's happening actually is that they put microvalves on the top here that are controlled by the frequency of the music. So certain frequencies will let through certain liquids, and other